Okay, 2.5 consists of two parts. The first part is implicit differentiation. The second part we are looking at definition of derivative and equations of lines. So kicking off our first part here with implicit differentiation, the question we are looking to address is how do we take the derivative of a function when the function has multiple variables? The process that we utilize to do this is called implicit differentiation, and there are 4 steps to it. Step 1, we are going to differentiate both sides of the equation with respect to whatever your independent variable is. For most of ours, it is going to be ddx. However, next semester, we're going to look at something called related rates, in which case we would be using ddt, because t happens to be the independent variable. It also could be dd theta, right? Just whatever that independent variable happens to be. We then are going to separate the dependent derivatives, the dy dx's, for most of our problems here in implicit differentiation, from the other terms. Again, recognizing that next semester this could be dA dt or dr dt or whatever the dependent variable happens to be that you're trying to solve for. In this case, we're, for the most part, solving for dy dx, our derivative. Right? If necessary, we will then factor out a dependent derivative, a dy dx. This would be if you had multiple dy dx's, you would factor one out, so that then you can solve for the derivative, that dy dx, which for most instances is going to mean usually divide. Okay? And this is so we still get that derivative, right? We've been practicing a number of different derivatives, and they all have dy dx equals, right? Or f prime of x equals, or something like that, right? We are getting it into that form of dy dx equals, so we can state what our derivative is. Okay? So I'm going to model these 4 steps in example 1 here, and then there are 3 more that we will use to practice. So example 1, find dy dx for 3x squared y plus y cubed equals 18x. Okay, so this would be an instance where we would want to use implicit differentiation because we're trying to find dy dx, but there's no easy way to get this function to just say y equals, the way all of our other functions have. Right? If we've been taking the derivative, we've had y equals, and then like 5x sine x or something like that, right? Because I can't somehow get this to just say y equals, we do have this multiple variables contained in our function. We're going to take the derivative as is, using whatever rules you would normally use. Right? So for example, in 3x squared y here, we see we have 2 functions being multiplied, and so we're going to use product rule. In y cubed, we have our power rule, and in 18x, we have another power rule with its coefficient out front. Okay, so let's go ahead and do product rule here. So 1d2 plus 2d1. So 1 is 3x squared. d2, the derivative of y, is 1 dy dx. Right? This 1 comes from the power rule. Right? Y has an exponent of 1. If I brought that 1 down in front, we'd have 1. Leave the base alone would be y. Subtract 1 from the exponent would be 0, right? 1y to the 0, okay, which is 1. And the dy dx comes because we've taken the derivative of y. Think about all of the equations that we have used so far. Right? Every single derivative we have taken, when we have taken the derivative of the y side of the equation, we have written dy dx, acknowledging the fact that I just took the derivative of my dependent variable, that I took the derivative of my y. You also could put y prime here if you wanted. Right? It doesn't matter which label you use, dy dx or y prime. Okay, so this is 1d2 plus 2, which is my y, d1, derivative of 3x squared, bringing down that 2, leaving the base alone, subtracting 1 from the exponent would be 6x. Okay, so that's product rule. Then we have our derivative of y cubed, which is bring down the exponent, leave the base alone, subtract 1 from the exponent, 3y squared, and then dy dx, because I just took the derivative of the y. Equals, and derivative of 18x is 18, right? Because this is 18x to the first, bringing down the exponent, subtracting 1 from the exponent, you get 18. The 2 most common mistakes when it comes, well, actually I'm going to say 3. 3 most common mistakes when it comes to implicit differentiation are all contained in this first step, and so we're going to take note of them right here, and I'm going to make them little notes off to the side. Heads up. Watch for product rule. Okay, that is by far the most common mistake. It's easy to miss product rule, but when you see that x and that y being multiplied together, it is product rule. Okay? 2. dy dx does not replace the y. Okay, notice when I did, for example, y cubed, it was 3y squared and then dy dx. Right here, derivative of y was 1 dy dx. The dy dx doesn't replace the y. It's an acknowledgement that I took the derivative of y. The same way we always have. We've always acknowledged we've taken the derivative of y by either putting y prime or dy dx equals. Right? That's not a different thought process there. But it's tempting to want to view it as replacing the y. It's not replacing the y. It's labeling your derivative. It's stating I have taken the derivative of y. The same way it always has. Okay, and then the last one, don't forget the other side of the equals. Okay, it's easy to accidentally leave this as just 18x, but again, remember that's not a new thing. We've always taken the derivative of both sides. Right? It's just one side has always been very straightforward. Y became dy dx because derivative of y is 1 and I took the derivative of y, so I acknowledge it with a dy dx, stating I have taken the derivative. Right? Like that. Again, we've always taken the derivative of both sides, but with implicit differentiation, I sometimes see students who forget the other side of the equals. Okay? After that, the next 3 steps are all algebra. We're going to separate the dependent derivatives from the other terms. And so I'm really quickly here just going to clean this up. 3x squared times 1 is 3x squared. We've got our 6xy. Okay. So separate the dependent derivatives from the other terms. Well, 18's already over here, but this 6xy doesn't have a dy dx attached to it. So I'm going to subtract that 6xy to the other side. Right? If necessary, factor out a dependent derivative. We do have, so let's put in parentheses here, if there are more than one dy dx, more than one dy dx, which there is here. So let's go ahead and factor that dy dx out. We have dy dx times 3x squared would be left in the first term when I pulled the dy dx out, and 3y squared would be left in the second term. And then solve for the derivative. Dy dx usually means divide. So I'm going to divide that over to the other side. So dy dx equals 18 minus 6xy, all divided by 3x squared plus 3y squared, which would be your answer. Okay? Other potential answers, well, they might have factored out a 3 or maybe even a negative 3, right? So if I factored out, let's factor out a negative 3. We would have 2xy minus 6 all over, factoring out a negative 3 in the bottom. It would be negative x squared minus y squared, and then those negative 3's could cancel, right? So maybe your answer would be 2xy minus 6 over negative x squared minus y squared, or maybe they just factored a 3 out, not a negative 3, and so all of these would have reversed signs then. Okay? So all of these are just other ways your answer could show up, again, for that multiple choice element. Okay. So we have 3 more of this to practice. My recommendation would be to maybe watch one more here with me or something like that, and then maybe pause the video and try them on your own, or maybe try example 2 and then watch example 3 and then try example 4, or whatever you feel like is going to be best for you. But I'm going to walk through all 3 of these. Again, make sure you're practicing at least some of it on your own, right? So you're getting that gauge. Where are your questions? What are you actually understanding or not understanding? Okay? So example 2. 3x squared plus y squared minus 6y equals 18. Find dy dx. Again, we see our multiple variables in here. There's no easy way to get the y by itself, and so I'm going to take the derivative as is. Okay? Derivative of 3x squared, that's power rule. Bring down the exponent, subtract 1 from the exponent. Okay, y squared, we have, again, power rule. Bring down the exponent, leave the base alone, subtract 1 from the exponent, and then I just took the derivative of a y, so I'm acknowledging that with a dy dx. The same way we always have. That's not new. We've always acknowledged that we took the derivative of a y by putting dy dx or y prime. Okay? Derivative of 6y would be 6. Right? Because remember, this is y to the first. Bringing that down, subtracting 1 from the exponent, we'd have a 0 in the exponent, which is 1. And so this would just be minus 6. Okay? And then derivative of 18, that's a constant. Oops, I missed something. What did I miss? Okay, I just took the derivative of a y, so I should have a dy dx there, acknowledging that I took the derivative of a y. Okay, and then on the other side, derivative of the constant is 0. Okay, again, every time we take the derivative of a y, we acknowledge with a dy dx. Okay? And then we're finding dy dx, so separate the dependent derivatives from the other terms. In this case, the 6x is the only one without a dy dx, so I'm going to subtract that to the other side. Okay? If necessary, factor out a dependent derivative. If there is more than one dy dx, which there is in this case, let's go ahead and factor out that dy dx. We'd have a 2y left over in my first term and a minus 6 in my second term. And then solve for the derivative. In most cases, divide. So I'm going to divide that 2y minus 6 to the other side. And there's your answer. Other things that might have happened, they might have factored out a 2. And simplified that. So maybe gotten negative 3x over y minus 3. Or maybe they factored out a negative 2. And if they had factored out a negative 2, this would be 3x over 3 minus y. Okay? So other forms that the answer could show up in. Okay? Example 3. Find dy dx for x squared sine of 2y equals x. Okay? So what do we have here? Well, we've got product rule, two things being multiplied together, and in here we've got chain rule for our d2. Okay? So product rule, 1d2 plus 2d1. 1 is x squared. D2, derivative of sine is cosine. And then derivative of the guts, derivative of 2y would be 2. And then I just took the derivative of y, so I'm going to acknowledge that with dy dx. Plus 2, which is my sine of 2y. D1, derivative of x squared, is 2x. On the other side of the equals, derivative of x is 1. Okay? And then I'm going to clean this up. We have our 2x squared cosine of 2y dy dx plus 2x sine of 2y equals 1. Step 2, separate the dependent derivatives from the other terms. Okay, so in this case that would mean subtracting that 2x sine 2y to the other side. And last but not least, solve for the derivative, because there's no dy dx to factor in this one, right? So we're just dividing the 2x squared cosine y to the other side. . And we are done. Okay, example 4, last one for implicit differentiation here. Again, if you have not tried one on your own, pause the video, try it on your own. Okay? Find dy dx for root y plus x cubed minus y squared equals 8x. Okay, so root y is the same thing as y to the 1/2, which is power rule, so let's bring down that exponent, leave the base alone, subtract 1 from the exponent. And then I just took the derivative of a y, so that would be dy dx. Okay, x cubed, derivative of x cubed is 3x squared. Y squared, derivative of a y squared is 2y. And then I just took the derivative of a y, so that would be dy dx. Derivative of 8x is 8. Okay? Step 2, separate the dependent derivatives from the other terms. So I'm going to go ahead and leave this 1/2 y to the negative 1/2 dy dx and the minus 2y dy dx on this side. And I'm going to subtract to the other side the 3x squared because that doesn't have a dy dx on it. Okay, if necessary, which this one is, factor out a dy dx. So we have 1/2 y to the negative 1/2 and minus 2y. And then last but not least, solve for dy dx. So we are dividing that 1/2 y to the negative 1/2 minus 2y to the other side. Okay? Which is the right answer, but most likely, as we've talked about in class, they would get rid of that complex fraction. And so if this were a problem, I'm guessing they'd multiply top and bottom by that 2 root y. Distributing that in, 8 times 2 is 16. 2 times 3 is 6. The 2 root y would cancel. And minus 2 times 2 is 4. And then either y root y or y to the 3/2, one of the two. Okay. Okay. Part 2 then of your 2.5 notes. So this was implicit differentiation. Again, write down any questions you might have now. You're going to forget them, right, by the time you get into class, or at least there's a good chance you will. And so I would write them down now while you're thinking about them. Okay? But the second part here is going to be definition of derivative and equations of lines. And I don't really have a guiding question for these. We've actually already seen definition of derivative before. An equation of lines is a chance to bring back some older concepts in math, so this isn't necessarily calculus, but making sure we are good to go with them. So this is, I'd say these two ideas here that are in your second half of 2.5 are kind of like tying up loose ends, right, to our lessons, to our unit. Okay, so definition of derivative. You first saw this in 2.1. I gave you the definitions of derivative, and the primary one we are going to be looking at here is the one that's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay? There is a second one that I also gave you in 2.1. It's the limit as x approaches a of f of x minus f of a all over x minus a. As we mentioned in 2.1, your job is going to be completely, in terms of the AP test, really only to be able to recognize them. You are going to see these in different forms, and they are going, you just need to be able to say when you look at them, oh, they're talking about a derivative, right? This is the definition of a derivative here, okay? And I'm going to demonstrate that with example 1 as we take a look at it. Okay? I've structured this so we do 1 together, 1 for you on your own, 1 together, 1 for you on your own. And these are pretty fast. Okay? Example 1. Limit as delta x approaches 0 of 2x plus delta x squared minus 2x squared all over delta x. So there's several things that are going to cue the definition of derivative. First of all, you're going to see some variable approaching 0. It might be delta x, it might be h, it could be p, right? It doesn't matter as long as it's approaching 0. In the denominator, you're going to see that variable, delta x or h or p or whatever the case may be, because that's in the denominator. And in the numerator, you're going to see two very similar looking functions being subtracted from each other, right? In one of the functions, you are going to see that variable that's approaching 0 combined with your independent variable, your x or whatever. And in the second function, the one behind the minus, you are only going to see the independent variable, not the one approaching 0. Okay? And when you see that pattern, like I said, that's going to need to cue, oh, they're talking about a derivative. Okay? In which case, you have two things you need to do. Step 1, you need to identify what your f of x is. Again, your f of x is the function itself, and it's always going to be located behind the minus. Okay, in some cases, you will have to factor out that negative so you can see the full function. In a case like this, we have our 2 something squared, our 2 something squared. There's nothing to factor out back here. And so I'm just going to look behind the minus, and behind the minus is 2x squared. Right, that's your f of x, your function there. Okay, and once you've identified what's behind the minus, again in this case the 2x squared, your second step is to take the derivative. What's the derivative of 2x squared? Well, bring down that exponent. You'd have 4, leave the base alone, subtract 1 from the exponent. So your answer is 4x. Okay? Which is all you will have to do. I do want to make sure that I prove why this works, though, or prove that there is another way to do it potentially. Okay, the limit as delta x approaches 0. If you didn't do this process of recognizing that it was the derivative, well then you would solve a limit the way we always have, which is plugging in the 0, we get 0 over 0. I can't get 0 over 0, right? So then I'm doing something else. In this case, maybe it's foiling out that x plus delta x squared. So we'd have x squared plus 2x delta x plus delta x squared. And then maybe distributing the 2 in. So we'd have 2x squared plus 4x delta x plus 2 delta x squared minus 2x squared all over delta x. Okay? Well, then we've got a 2x squared and a minus 2x squared, which are going to cancel. Okay? And so we are here at 4x delta x plus 2 delta x squared over delta x. And then I notice there's a delta x in common in the numerator. So maybe I factor that out, 4x plus 2 delta x. Okay? Well, delta x divided by delta x is 1. They cancel. And then delta x is approaching 0, so now when I plug it in, I get 4x plus 2 times 0, which is just 0, and 4x plus 0 is 4x, which is the same thing you get by just taking the derivative of your f of x. Okay? Again, we want to be able to do this. It's a whole lot faster, right, than walking through our limit process. But it does require us to be able to recognize the pattern involved in this definition of derivative, which again is everything we talked about at the beginning of this. Okay? Okay, so I would recommend pausing the video, try an example 2 on your own, restarting it when you have an answer. Okay? Example 2, we see our little setup here, looks like definition of derivative. Okay, so I'm going to go ahead and do identify my function. My function is what's behind the minus, and again, you might need to factor out a negative. In this case, they've already factored the negative out, right? I already have my parentheses here, so I can see my function behind the minus there. And so my function is 3x minus 5. And then taking its derivative, derivative of 3x is 3. Derivative of 5, a constant, is 0. And so my answer is 3. Or you can walk through this whole process with it. But again, that's a lot of time to take when you don't need to. Okay? Example 3, let's do example 3 together here. We have limit as h approaches 0 of this thing. Again, we see our pattern like what we would expect from definition of derivative. I've got a variable approaching 0, right? I see that variable in the denominator. Up in the numerator, I see two very similar setups, one with an x or some independent variable and the variable approaching 0, one without the variable approaching 0, and sure enough, I see that. I've got something cubed, a 2, something squared, a 5. Here's something cubed, a 2, something squared, and a 5. Right? So that's similar setup in the numerator. Pulling out my function here, the one thing we do need to be careful of is in this limit, they haven't already factored the negative out. This is, I would say, the hardest that this type of problem gets is when you have to factor the negative. Okay? You just have to catch it. So we have x plus h cubed minus 2x plus h squared minus 5. Factoring this negative out back here, the negative x cubed would be positive x cubed, the positive 2 would be negative 2, and the positive 5 would be negative 5. We do that for two reasons. One, so that we can see our function. Our function is now x cubed minus 2x squared minus 5. The second reason is so that they actually match, right? This minus 5 and this was a plus 5. Well, now they're both minus 5. These are both minus 2 something squared. These are both positive something cubed, right? It's so we actually get matching functions with the subtraction sign in between, which is our setup for our definition of derivative. Okay? And so then taking the derivative, derivative of x cubed is 3x squared. Derivative of 2x squared is 4x. Derivative of 5, which is a constant, is 0. Okay? Go ahead and pause the video, give example 4 a shot, restart it when you are ready. Okay, example 4, again, we do need to factor out our negative here. So they actually match. Sine of x plus delta x minus 9 of x plus delta x to the 4th. Minus, and then the negative sine x would be positive sine x, and the positive 9x to the 4th would be negative 9x to the 4th. So that I can actually see my function. My function is sine x minus 9x to the 4th. Okay, and so what's the derivative? Well, derivative of sine x is cosine x. And derivative of 9x to the 4th is 36x cubed. Okay? Oops, a little bit off the screen, sorry about that. 36x cubed. Okay, so that's definition of derivative. They're pretty quick problems. We'll do some more practice with them, obviously, in class. And then the last little wrap-up thing is going to be our equations of lines. So equations of lines is a very common both multiple choice and free response question. You will see something that asks you to write the equation of the line tangent or the equation of the line normal to. Okay? So we're going to do both here. Now for both, we do write in point slope form. Right? So y minus y1 equals m times x minus x1. Okay. This is going to be from my point, because you'll always either be given a full coordinate point or at least an x value that you can use to solve for y. And then slope, what is slope the same thing as? Back from unit 1? or sorry, from lesson 1. Slope is the same thing as derivative, right? And so I'm going to be putting my derivative with point plugged in into that slope spot, and you'll have your equation. Okay? And then throwing this in, because I find every year I have some students who have heard this word, some who have not, and so making sure we are all on the same page. Normal. So normal line is perpendicular to tangent line. Which means what? What does that, I know we know what perpendicular looks like, but in terms of my equation, what does it mean for two lines to be perpendicular? What's going to change about my two equations to create a perpendicular equation? And I'll give you a hint. It has something to do with the slope. What's true about the slope of lines that are perpendicular? You remember? They're opposite reciprocal, which means opposite reciprocal slopes. And we're going to practice both in the 4 examples below, so that you can see that difference, make sure we really are good with what normal means. Okay? Okay, let's go ahead and practice. So 4 examples. Again, I'm going to do one. I would recommend watch 1 or 2 with me, but again, at some point, make sure to pause the video, try it on your own. Okay? So find the equations of the lines tangent and normal to. So I'm going to go ahead and put my tangent here and my normal, and I'm going to set up their form. Y minus y1 equals m times x minus x1 for my 2 equations. And they are going to be tangent and normal to this equation, negative x squared y plus 2y equals negative 2, at x equals 2. Okay, so I've got, first off, one part of my point, my x coordinate. Question then becomes, well, they didn't give me a y coordinate. Okay, how could I find a y coordinate? Well, I've got an equation, and I've got what x equals. So I could plug it in. Okay, plugging in that 2, we would have negative 2 squared, which is 4y, plus 2y equals negative 2. Negative 4y plus 2y is negative 2y, which equals negative 2. And dividing that negative 2, we get y equals 1. And so I have a coordinate point here of 2, 1. Okay? And then I need my slope. Well, slope means derivative. So I'm taking the derivative of this function. Okay, our variables are all mixed up here, so let's go ahead and use implicit differentiation. So we have 1, negative x squared, d2, which is 1, and then I just took the derivative of a y, plus 2, which is y, d1, negative 2x, plus derivative of 2y is 2, and then I just took the derivative of a y, equals, and derivative of negative 2 is 0. Okay? Separating my dependent variables from the other, we would have negative x squared dy dx, and then I'm going to leave this 2 dy dx over here. Add the 2xy to the other side, because that one doesn't have a dy dx. And then factor out the dy dx. To divide. dy dx then equals 2xy over negative x, over negative x squared plus 2. Okay, and so that's my derivative. So slope is the derivative with the point plugged in. So I'm going to plug in my 2, 1 here. My numerator, therefore, I'll go ahead and do this, m equals, my numerator would be 2 times 2, which is 4, times 1, which is 4, over negative 2 squared, which is negative 4, plus 2, which is 4 over negative 2, or negative 2 for my tangent line. And then normal is perpendicular to tangent, which means opposite reciprocal. And so the negative is going to become a positive, and flipping that 2 is going to be 1/2. Okay? Okay, so there are 3 more. Again, if you want to watch another one, go ahead and do so, but at some point pause the video, try it on your own. Okay? Example 2, write the equation of the lines tangent and normal. So let's go ahead and set that up. Tangent and normal. Y minus y1 equals m times x minus x1. Okay? And we are finding them to this equation at x equals 1. So I've got my x. Don't have a y, but I can solve for y. I've got an equation and an x value. That's all I need. So plugging my x in, 1 cubed is 1, plus 3 times 1 is 3y equals 10. Subtracting the 1 over, we get 3y equals 9, which means dividing the 3y equals 3. Okay. And then derivative for my slope. Derivative of x cubed is 3x squared. We've got product rule back here. Our 1, 3x, d2, derivative of y is 1, dy dx, plus 2, which is y, d1, derivative of 3x is 3, equals derivative of 10 is 0. Okay, I'm going to leave this 3x dy dx on this side and subtract the 3x squared over and the 3y over, and then divide the 3x. Okay, and so then our slope is our derivative with our point plugged in, so m equals, my point here is 1, 3, right? X equals 1, y equals 3. So x equals 1, negative 3 times 1 squared is negative 3, minus 3 times 3 is 9, all over 3 times my x, which is 1, which is 3, which is negative 12 over 3, which is negative 4. And so then what would your normal equation be? Or normal slope? Opposite reciprocal, so the negative would be positive, and flipping that 4 would be 1/4. Okay? 2 more again. Make sure you're pausing the video, trying them on your own at some point. Tangent and normal. Y minus my y1 equals m times x minus my x1 for both. Okay, tangent and normal 2, f of x equals 3x squared minus 5 at 322. Yay, example 3 is a nice one. They gave us both our x and our y coordinates, so we're going to plug our x and our y in. Okay, and then slope means derivative, so let's take the derivative of this function. Derivative of f of x is f prime of x. Derivative of 3x squared is 6x, and derivative of 5 is 0. Okay, and so then plugging in, my slope is 6 times my x is 3, which is 18. Okay, and so what would your normal slope be? Okay, well, opposite reciprocal, positive would become negative, and flipping that 18 would become 1/18. Okay, last but not least, example 4. Tangent and normal. Y minus my y1 equals m times x minus my x1. Okay, and we are tangent and normal to this function at x equals 3. Okay, so we have our x, need our y, so let's go ahead and plug that in. G of 3, my y then would equal 3 divided by 3, which means my y equals 1. Okay. Derivative then for my slope, derivative of g of x, g prime of x. And then over here you have options. You could do quotient rule, or you could do power rule if you rewrote this as 3x to the negative 1. Then you could just do power rule if you wanted. They both work, both result in negative 3 over x squared. Whether you do quotient rule or power rule, doesn't matter. And then getting your slope, plugging my, in this case I only need my x, so my 3 in, I get negative 3 over 3 squared, which is 9, which is negative 1/3. And so what would my normal slope be? Okay, opposite reciprocal, so negative becomes positive, and flipping that 1/3 would be 3. Oh, my pen's dying. There we go. Okay, so that is 2.5. Again, write down any questions you might have, and we will talk about them in class.